All right. So we're looking at 12.1 today, the counting principle. May be able to get into 12 too. We'll see. So an experiment is an activity. Let me write that activity better. Activity with an observable outcome. So an example of that is flipping a coin. That would be your experiment. Sample space, all possible outcomes of an experiment. So if we're talking about flipping a coin, heads and tails would be a sample space. Also notice that it's usually denoted by S. All right, an event would be any collection of outcomes from the sample space. So an example of that would be tails. So if I want to know what's the probability of landing tails, tails would be my event. All right, and that's usually denoted by a capital letter. And what letter you use normally is reflected upon whatever the event is. Maybe you'll call the event tails or T for tails, but it's up to you. The one that normally is used is this S, and that's for sample space. That's the one that's normally have a usage already. The other ones you can just use whatever letter you like. All right. Trying to make sure everybody's clear of event before I scroll up. All right, first exercise. One number is chosen from the sample space, and they give us 1 through 10. And it says list the elements in the following events. All right, well, I already have the answer there. I was going to erase it and everything, but it's not necessary. So A, the event is the number is even. So when you look at your sample space, 1 through 10, what numbers are even? And so that would be 2, 4, 6, 8, and 10. So each number is an element. So when it says list the elements in the following events, so you're talking about what elements are described in that event. Next one, the number is divisible by 5. So the only two numbers that are divisible by 5 in our sample space is 5 and 10. And then C, the number is prime. So you're talking about prime numbers that are in this list. So 2, 3, 5, and 7. And prime numbers are numbers that can only be divided by 1 and itself. All right, any questions? All right. Next exercise. Two-digit numbers are formed from the digits 1, 3, and 8. Find the sample space and determine the number of elements in the sample space. So the easiest way to handle this type of problem is to create a chart where we're using 1, 3, and 8 to create all of the two-digit numbers that involve 1, 3, and 8. So the first one is 1 and 1. Then we have 1 and 3, 1 and 8. Then we do 3, 1, 3, 3, 3, 8. And then last row will be 8, 1, 8, 3, and 8, 8. So those will be all of the numbers that can be created, all of the two-digit numbers that can be created by 1, 3, and 8. And there are 9 elements or 9 numbers in that sample space. All right, any questions? All right, so of course this one didn't have these. Just started off like this. A true-false test consists of 10 questions. Draw a tree diagram to show the number of ways to answer the first 3 questions. All right. All right, so put that one back. Yep. So key thing here is that they tell us to draw a tree diagram, and we're only looking at the first 3 questions. All right, even though it's a 10-question test, we're only looking at the first 3 questions and how we can answer the first 3 questions. So here's my tree, probably don't, yeah, well, it's okay. So your first question, if you decide to answer true first, then you have the choice of going true or false. Then from each one of those questions, you can go true or false, right? Then the same thing happens down here. If you decide to answer false first, then from the false, you would do true or false. And then from each one of those responses, true or false. So you're just creating a tree that represents all of the possible outcomes of answering the first 3 questions of your true or false test. And then here's just the responses in a list: true, 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 false, and so on. Any questions? Any questions? All right, anybody else? Everybody good? Okay, good. So now we're looking at the fundamental counting principle. And it states if you can choose one item from m items and one item from n items, the number of two item choices is m times n. So let's write that down before we look at an example. All right, looking at the first exercise right here to implement the fundamental counting principle. If you have 30 shirts, 20 pairs of jeans, and 10 pairs of shoes, how many different outfits could you create? So we're assuming that you're only going to wear one shirt, one pair of jeans, and one pair of shoes, right? So if that's the case, and that means we can use the fundamental counting principle. You're only choosing one item out of each category. Then all you do is multiply 30 times 10 times 10, 30 times 20 times 10, excuse me, which would be 6,000 outfits. So we see in the green, it says multiply the number of options in each category. 30 shirts, 20 pairs of jeans, 10 pairs of shoes. So you have 6,000 different outfits. So next time you say you didn't have anything to wear, there's probably a combination out there that you hadn't thought of yet. Any questions? All right, you scroll up. Good. All right, so the next one, in horse racing, betting on a trifecta refers to choosing the exact order of the first three horses to cross the finish line. If there are 8 horses in a race, how many trifectas are possible, assuming there are no ties? All right, so when we talk about doing this, initially you would set up your boxes, first, second, and third, So in each place, you will put how many options you have. So when you look at first place, you have 8 horses altogether. You have 8 horses altogether. So you ask yourself, how many choices do I have to come in first place? And that would be 8. Now, after one horse crossed the finish line, you have 7 horses left that could possibly come in second place. And then after that horse crossed the finish line, there are 6 horses left that could come in third place. So that's why we have 8, 7, and 6. What you put in your box is the number of options you have for each category. Once again, we have 8 horses altogether. So when it comes to first place, there are 8 different horses that could possibly come in first place. Once that horse crosses the finish line, first place horse, now there are only 7 horses left that will be able to come in second place. After that horse crossed, now there are only 6 horses left that could possibly come in third place. Once you establish that, 8 times 7 times 6 is what you would do, and you have 336 possible trifectas. All right, questions, questions, questions. All right, next example. It says from the letters A, B, C, D, and E, how many four-letter groups can be formed if? Then they give us a few to try to figure out. Put that back. So let me erase this, make sure we're okay with it. All right, so we want to know how many four-letter groups can be formed. And in A, it says if a letter can be used more than once. So we have 5 letters altogether. So in each box that represents, we're trying to find, 4-letter groups. So that's why I have 4 boxes. So if I could use my letters more than once, that means in each box, I would have 5 choices. And then you multiply that number 5 to itself 4 times, and that'll give us that 625. But that's why it's 5 each time, because each letter can be used more than once. And then in B, you see the difference. Each letter can be used exactly once. So in the first box, I have the option of my 5 letters. Once I use that letter, then in the second box, I have a choice of using 4 letters. Then once I use that, I have 3 letters left. And then in that last box, there are only 2 letters that I could use or choose from. And then 5 times 4 times 3 times 2 gives us that 120. All right, questions? Any questions? So before we look at least start 12.2, questions on anything I said out of 12.1?
No.
All right, thank you, thank you. Is everybody good? Can I leave the screen?
Oh, I do got a question though.
Yeah,
For the test reviews, we have multiple um options, right, to keep guessing the right answer.
yeah, uh-huh,
Okay, okay.
yeah. I hope you wouldn't just be over there just guessing though. Let's see, I just messing with you. So you mean to tell me that 4 number iPhone password, 10 possible? Yeah, yeah, yep. Because we got 10. Yep, 10 times itself 4 times. Yes, sir. Good, good, good connection. Good connection. Let's see. All right, permutations and combinations. Okay. So let's go ahead and get into 12.2. We can start it. We may finish it, may not. But 12.2 permutations and combinations. So we start off talking about factorials. So exclamation point in mathematics is a factorial. So we just letting n represent any number right now. We'll put a number on it in a second. But what you would do is whatever number that you're using, you just count down by ones all the way down to 1 and multiply those numbers together. So if you had 100 factorial, 100 exclamation point, that would be 100 times 99 times 98 times 97 times 96, all the way down to 1. And you'll multiply those numbers together. So 1 factorial is equal to 1. Then also 0 factorial is equal to 1. There's a proof for that. I'm pretty sure y'all don't care about it, but it is a legit mathematical proof that 0 factorial is equal to 1. All right, so simple example of how factorial is used. Right here, if you have 4 factorial or 4 exclamation point, that's going to be 4 times 3 times 2 times 1. So like I said, you take the number that you see initially, count down by ones all the way to 1, multiply all of those numbers together, and that'll be 24 in this case. All right. All right, so let me erase some of this stuff so we can walk through it. All right, so they tell us to evaluate. Of course, this part wouldn't be here. It would just be 8 factorial over 5 factorial. So we'll talk about the long way of doing it and then the short way of doing it. So the long way is to expand it out. Here we have 8 factorial, which is 8765431. And we have 5 factorial, which is 54321. So what we notice is that, remember when you're dealing with fractions and canceling out whatever's in common with the top and bottom can cancel. So we have 54321 that's in common with the top and the bottom. So those numbers will cancel out for us, leaving us with 876. So 8 times 7 times 6 will give us this 336. All right. Any problem with that?
No.
All right. Thank you. Thank you. So now the short way. Notice that we have this block of numbers that cancels out with this block of numbers. That represents 5 factorial. So within the 8 factorial is, 5 factorial. So what we can do is look at it this way. We would take the 8 factorial down to just 5 factorial because that's what was in common, or that's what we had down here. And then cancel that out because we know that's what will ultimately happen anyway. That 5, 4, 3, 2, 1 exists inside of that 8 factorial. So those cancel and then leaves us with just the 8 times 7 times 6, which is 336. Excuse me, I had to sneeze. So it's important for us to see that way because what we don't want is to have to write out all of our numbers like in this next one. So if we had 100 factorial over 98 factorial, we don't want to have to write 100, 99, 98, 97, 96, 95, all the way down to 1. So all we do is recognize that we have 98 factorial right here, and we just take the 100 down to just 98 and cancel that out with what's in bottom. And that leaves us with 100 times 99, which is 9,900. All right. So now something like this, 5 factorial minus 3 factorial. What we cannot do is subtract them in their current state and do 5 factorial minus 3 factorial, which will give us 2 factorial. So that's not how that works. So this is a separate application than this one. So what we have to do is to go ahead and expand both of those out. How do I do that? Probably should have kept them. This 5 factorial is 5, 4, 3, 2, 1. And that 3 factorial is 3 times 2 times 1. Multiply those out, that's 120 minus 6, and that'll be 114. All right. Make sure we are good. All right, so we're gonna look at permutations and combinations. So permutations are arrangement of items in which the order matters. So that's going to be the key distinction between the two when we talk about permutations and combinations. Permutation, the order matters. So this is the formula right here. Now, you don't necessarily have to know how to do this formula. You should have a calculator or have access to a calculator that can do this for you. Even if you do, just go on Google and type in permutation calculator. Like, you don't really need to, lean on this formula right here. All right. I'm going to show it to you anyway, just in case somebody wants to use it. But there's in your calculator, you probably can see a button that does this. It looks like this, or it may even be a square and another square. But majority of scientific calculators have the permutation and combination, options. So if you ever have any questions, always feel free to either shoot me a picture of your calculator, or we can meet in a Zoom session outside of class and see what your options are for your calculator. But most scientific calculators has this as an option, and all you need to do is know what N is and what R is, and you'll be good to go. And once again, even if you don't have that calculator, you can Google permutation calculator, and it will do it for you. So notice this permutation of N things taking R at a time. N is always going to be a larger number. And so what they mean by R at a time, let's say if I have a classroom of 30, and I want to know, and I'm going to choose 5 out of 30 students to go on a trip. I don't know. So how many different ways could I choose 5 out of 30? So you're talking about the permutation of 30 students taking 5 at a time. And that N is always going to be a larger number. All right, so university tennis team. I'll write that V better. University tennis team consists of 6 players who are ranked from 1 to 6. Write that a little better. Who are ranked 1 through 6. If a coach has up to 10 players from which to choose, how many different ranked teams can the coach select? So notice we have a ranking from 1 through 6. So that means the order matters. Order matters. So that's how you know you'll be using permutation, when the order matters. It says how many different ranked teams can the coach select? He has 10 players altogether. He want to choose 1 through 6. So he's going to be trying to figure out how many different ways could he choose 6 out of the 10. So that means N is 10 and R is 6. Remember I told you N is always going to be the larger number. So that's going to be 10 factorial over 10 minus 6 factorial. Do what's in the parentheses first. 10 minus 6 is 4. And that'll be 10 factorial over 4 factorial. Cancel out the 4 factorial. That leaves you with 10, 9, 8, 7, 6, 5. Multiply those together. You have 151,200 different ways you can create a team of 6 out of those 10 players. All right, any questions? Make sure we're good. All right, next one. In 2015, 18 horses were entered in the Kentucky Derby. How many different finishes of first through fourth place were possible? So once again, we have a ranking first through fourth place. So once again, we're using permutations because the order matters. 18 horses altogether, 4 places. So that means N is 18, R is 4. That'll end up being 18 factorial over 18 minus 4 factorial. 18 minus 4 is 14. 18 factorial over 14 factorial will give you 73,440. All right, any questions? All right, next one. 5 women and 4 men are to be seated in a row of 9 chairs. How many different seating arrangements are possible? All right. So the first one, how many different seating arrangements are possible if there are no restrictions on the seating arrangements? So 5 women, 4 men, 9 people altogether. Doesn't matter how you sit them. No matter doesn't matter how they're ordered. And so if we were to look at it this way, we have 9 seats. Remember, like we did before, we place the number of options in each box. So in the first seat, let me go get the first seat. I have 9 people to choose from, so that's 9. Once that one person sit down, 8 people to choose from. Then 7 people to choose from, 6 people to choose from, and so on, all the way down to 1. So set up your 9 chairs. You have 9 people to choose from out of that first box, out of the first chair. 8 people to choose from the second chair because that first person just sat down, and just do your countdown. Multiply those numbers together, get 362,880. All right, any problems? All right. So the next one, the stipulations are that the women sit together and the men sit together. Doesn't matter whether it's the men that sit first, then the women, or women that sit first, then the men. So first one we're going to explore is the women sitting together, then the men. So got our 5 chairs set up. Now there are 5 women, so we have our 5 chairs. So we do our 5, 4, 3, 2, 1 for the women. Then for the men, we do our 4 chairs, 4, 3, 2, 1, because there were 4 men. So you multiply those numbers together and we get 2880. So then we have to explore the idea that the men sit first, then the women. It's the same numbers, it's just that the 4 seats. First 4 seats are men, and then the next 5 seats are the women. But notice it's still 4, 3, 2, 1. 5, 4, 3, 2, 1 for the women. Multiply those together, you're still going to get 2880. And then to finish it off, we add the 2880 plus the 2880, and that gives us 5760. That's our final answer. So it's 5,760 ways that you could sit the women together and the men together without any interruption. All right. Any questions? Any questions? Okay. Let's go back. So combinations, a collection of objects in which the order does not matter. So order does not matter. I think I want to write that better. So remember, permutation, the order did matter. Combination, the order does not matter. So the formula for combinations is going to be similar, but it has this extra r factorial down here that the permutation didn't have. Once again, I'll use it a couple of times, show you how it worked, but combination formula, the use of it anyway, the calculation of combinations, is something that we're not emphasizing the formula, but emphasizing the fact that you do need a way to calculate that. So whether it be through your calculator or through a website or an app, make sure you have something reliable that can calculate permutation and combinations for you. Same letters, N and R, combination of N things taking R at a time. N is going to be the larger number of the two. So, an emergency room at a hospital has 11 nurses on staff. Each night, a team of 5 nurses is on duty. And how many different ways can the team of 5 nurses be chosen? All right. So you have 11 nurses. You're choosing 5 out of those 11. So N will be 11, R will be 5. That's 11C5. So 11 factorial over 11 minus 5 factorial times 5 factorial. So 11 minus 5 is 6 factorial. I just put a parentheses there. If somebody wanted to put in a calculator that way, just remember to put parentheses around the 6 factorial and the 5 factorial. But that's multiplication there. And if you do that, you should get 462 different ways. Any questions? All right. Next one, committee of 5 is chosen from 5 mathematicians and 6 economists. How many different committees are possible if the committee must include 2 mathematicians and 3 economists? Give you a chance to write that. All right, so we have 2 different categories here. We have mathematicians and we have the economists. So 2 of our committee, 2 people from the committee will come out of the 5 mathematicians. 3 people out of our committee will come from the economists. So we're going to set it up 2 different ways. So notice here, I did 5C2 because we wanted, once again, if you look at my line and my purples, we have these 2 mathematicians. They can't come out of the economists. They're only coming out of mathematicians. So that's where the 5 come into play. And then we have 6C3, in which those 3 economists will come out of the 6 that we had to choose from. So 5C2 is 10, 6C3 is 20. Multiply those 2 numbers together and we'll get 200. All right. Questions? Any questions? And okay, that's it. So that's 12-1, 12-2. Questions on anything that I said? Sorry about that. I had to sneeze. Everybody good before we close out today? Not going to jump into anything else, even though we had time. There's no rush on it like that, but we knocked out 2 sections, so that's a good place to be. Any problems? Any problems? All right. So try the stuff out. See if you get stuck on anything. We'll have those opportunities for you guys to ask whatever questions you want, whether it be at the end of class or on the review day. So make sure you try the stuff out and start tallying up the questions so we can knock them out. Outside of that, if you guys are good, I'm good. And I'll see you on Thursday.
I got a question.
Yep.
How did you just get 20?
Put it in the calculator.
Okay.
Yeah. Now, if you're talking about the actual process,
Yes.
doing it like this, that goes back to that formula right here. Oh, what in the world? All right. All right. Yeah, so I'm leaning on this formula. That's why I put everything where I put it. So N is 6 and R is 3. All right. So going back here. Now, the first thing I would do is 6 minus 3, which is 3. And then I would be looking to cancel out some stuff. So 6 factorial is 6 times 5 times 4. And I will cancel out that and expand this. So this 3 factorial cancels out with this one. And then 3 times 2 is 6, which cancels out with this. And so what you're left with is just 5 times 4, which is 20. So if you're doing it by hand, then that's how you would go about knocking it out. Now I will say, and I'll go back to it if you're copying it out, copying it down. If you have something like this, it will be more numbers because you're going dealing with 11. And and basically if you have larger numbers, then it would be more of a process. But yeah, but that's how you would do it.
Okay, thank you.
Yep, not a problem. And once again, I'm not holding anybody to this process, but you do have to find something that will implement that process for you. The book is not holding you to that process either, but they do want you to make sure you have something that enables you to be able to calculate that. I can't even say what the book is. I might be thinking about another book. I just know I'm not holding you to it, but I am holding you to having something that can do it for you reliably. All right. Anything else before we close? Everybody good? Everybody straight? All right. So you guys have a good one. Be safe, and I will see you on Thursday.
Have a good day.
Thanks. You do the same.